Every day, you're hit with all sorts of claims, right? This new diet works, this marketing slogan is true, this new policy is effective. But how do we actually know what's real? How do we separate the facts from the fiction? Well, that's where a really powerful tool called hypothesis testing comes in. And in this explainer, we're going to break down exactly how it works.
I mean, think about it. How does scientists know for sure if a new drug is safe to put on the market? How does a company prove its product is better than the competition? We need a way to move beyond just gut feelings or clever advertising and use cold, hard data to find an answer. That's the core problem we're going to tackle.
Okay, to make this all feel a bit more real, let's follow a single case from start to finish. Imagine researchers have developed a promising new antibiotic, but there's a huge question they have to answer: is it safe? Specifically, they're worried it might have a dangerous side effect on the kidneys. They're looking at something called serum creatinine levels, basically a number that tells you how well your kidneys are functioning. The health of a lot of people could be riding on this.
So, what is hypothesis testing, really? At its core, it's a formal, structured way to test a claim. And honestly, the best way to think about it is like a courtroom trial. Seriously, we have a claim that's on trial, we gather evidence, and then we reach a verdict. This whole courtroom analogy is going to be our guide through the entire process.
All right, so every courtroom has two opposing sides, right? In our statistical courtroom, it's no different. We have the null hypothesis and the alternative hypothesis. Think of the null hypothesis as the defendant. It's the default position, the status quo. It's the assumption that there's no effect. For our drug, the null hypothesis is that it does absolutely nothing to kidney function. On the other side, you have the alternative hypothesis. That's the prosecutor, making a new claim, arguing that yes, the drug does have an effect.
And just like a real trial, this process follows a very clear 5-step procedure. We've already done step 1, stating our two opposing hypotheses. So now let's walk through the rest of these steps and see how we actually reach a verdict on this new drug.
And this next point is absolutely crucial. The great statistician R.A. Fisher put it perfectly. We test the null hypothesis under the assumption that it is true. What does that really mean? It's simple: innocent until proven guilty. We start our trial by assuming the drug has no effect. The entire burden of proof is on the evidence, the data, to convince us otherwise.
Okay, step 2. We need to set our standard of proof. Our beyond a reasonable doubt line in the sand. In statistics, this is called the significance level, or alpha. A really common standard, and the one we'll use, is 0.05, or 5%. What this means is that we are demanding evidence so strong that you'd only see a result like it by pure random chance 5% of the time if the drug was truly harmless.
So, picture this bell curve. This is our courtroom. See that big area in the middle? That's the innocent zone. If our evidence lands in there, we don't have enough to convict. But look at those little red areas on the edges, in the tails. That's our guilty zone, or what we call the rejection region. If our evidence is extreme enough to fall in there, we can reject that no-effect claim. And with our 5% standard, the boundaries for that region are set at -1.96 and +1.96.
All right, on to step 3. It's time to calculate the actual evidence. So the researchers in our case gave the drug to 36 patients and they measured their results. Now we plug those results into this formula to get what's called a z-score. Don't worry about the math here. Just think of the z-score as one single powerful number that tells us how unusual our result is. It boils down all of our evidence into one number.
And so, after running the numbers, that single powerful piece of evidence is 3. So, the big moment. Where does our evidence fall in the courtroom? Well, our z-score is 3. Remember, the line for the rejection region was 1.96. So a score of 3 isn't just past the line, it's deep inside the rejection region. The verdict, you could say, is pretty clear. The evidence is just overwhelming.
And that brings us to step 5, the official conclusion. We formally reject the null hypothesis. In plain English, we have strong enough evidence to say that this antibiotic does, in fact, have a statistically significant effect on kidney function. Our trial is over. We have our verdict.
But wait a second. This is statistics, right? It's not magic. It's based on probability. So just like in a real court, even with a strong process and what looks like solid evidence, is it possible for the verdict to be wrong? And the answer is absolutely yes. A mistake can happen. This chart here lays out the 2 ways our statistical verdict can go wrong. We can have what's called a type 1 error, which is when we reject a null hypothesis that was actually true. Or we can have a type 2 error, where we failed to reject a null hypothesis that was actually false.
Let's stick with our courtroom analogy, because it makes this super clear. A type 1 error, or a false positive, is like convicting an innocent person. We thought the evidence was strong enough, but we made the wrong call. A type 2 error, or a false negative, is the opposite. It's like letting a guilty person walk free. The evidence just wasn't strong enough for a conviction, even though there really was an effect. Understanding this trade-off is just so important.
Okay, so let's wrap this all up. What are the big things to remember? First, always think of hypothesis testing as a structured court case for your data. Second, the null hypothesis, the no-effect claim, is always innocent until proven guilty. Your significance level is your standard of proof. The test statistic is your key piece of evidence. And finally, the conclusion is your verdict. But, and this is a big but, it's a verdict that's never 100% certain.
And that leaves us with one last kind of tricky question to think about. We reached our verdict using that 5% standard of proof. But what if we'd been even stricter? What if we demanded a 1% standard? Would our verdict have stayed the same? It really makes you wonder. When we're making decisions with data, how much proof is ever truly enough?